All right. So today there is not going to be a quiz, but what I put together are some problems focusing on the most recent convergence tests. So those are really the alternating series test, the ratio test, and the root test. So those are kind of the usual spot on Canvas. In the lab notes, we have the problems and the solutions. I think maybe it was the solutions, the pages were flipped in the PDF. So just all the problems are in there, but a little bit out of order. So I'll split you guys up into some study rooms and try these problems out, or take the solutions, take a look at the solutions as you need to. Again, there won't be a quiz, but getting comfortable with these tests is going to be especially important as we're talking about the new power series stuff. Sort of the idea of checking if a series converges using these tests is sort of the foundation of being able to ask these more difficult questions about when you have a power series, where does it converge? So I'll split you guys up into some rooms, and then I'll kind of pop back and forth. And after 25 minutes or something, we'll come back and go over all the problems together. So hold on just a sec. All right. So let's talk about these. Were there any that you would especially like to talk about, just to make sure we are able to spend enough time on them? Or just start at the beginning and go to the end and then stop? Okay, we'll do that one. So the first problem, n squared over e to the n. In all of these, I would say if you feel pretty comfortable with how the solutions go, also take a little bit of time to think about why. So you picked some test, you figured out whether it converged or diverged. It's good to spend a little time to think about why that test really was the best one and why some other tests might not be as good. So in this case, n squared over e to the n, I think, so it's not geometric, it's not a p-series. You could try the integral test. I think you can use integration by parts twice. So that's, if we can avoid it, not so good. It's definitely not alternating. One thing you might think about is what happens with the limit comparison test, or I guess either comparison test. And if you try that out, I don't think it ends up working because you would, if you're going to try to compare it to something, you would guess, let's compare it to 1 over e to the n. E to the n is much bigger than n squared. So you'd say, let's think about if this looks like 1 over e to the n, which is geometric. But then the problem is that, well, first, n squared over e to the n is bigger than this. Sorry, that's not equals, that's divides. N squared over e to the n is bigger than this, so you can't do a direct comparison. If you're bigger than something that converges, you could go either way. But also, if you try the limit comparison, that doesn't end up working either, because that gets you that the limit would be infinity, and that doesn't help either. So the comparison tests don't work. So we've seen series not too dissimilar to this where we did a comparison, but in this case, it doesn't really work. So, but then what does work is actually the ratio test or root test. Both of them work pretty well. The ratio test, because exponentials and polynomials, those are powers of things. So the ratio test is good for that. Powers and multiplication. Root test, because you have things raised to the exponents, that's good. So the ratio test says, well, it's positive, so the absolute value doesn't do anything. But you have just these terms on the bottom of your fraction. Let me zoom in a little bit. Here we go. The terms on the bottom, and replace the n's with n plus 1 on the top. Then you flip and multiply, and when you do that, you group things, putting the exponentials together and the polynomials together. The exponentials get some cancellation to be 1 over e. Over here, we don't really get cancellation, but what we do get is a rational function, and they have the same power. They're both n squared. And so this is fixed, that's just 1 over e, and this limit goes to 1. So the limit is 1 over e, then you have to look up in the ratio test, what does that mean? For the ratio and root test, the dividing line is 1. And if you're smaller than 1, the series converges. If you're bigger than 1, it diverges. So our limit was less than 1, so it converges. The root test, we set up a different limit, but we end up in a pretty similar place. We take the nth root of n squared over e to the n. On the bottom, the nth root of e to the n, that cancels to be just e. On the top, we get the nth root of n squared. And here you can either use some exponent rules to rearrange things a little bit, but maybe the more general fact that's going on is the nth root of polynomial goes to 0. And that's what we have here. So the top, doesn't go to 0, it goes to 1. So the top goes to 1, the bottom doesn't have any n, so that's e. So we get 1 over e again, and by the same reasoning, that's less than 1, so this series converges. And in doing this, you just have to pick one test. There might be more than one. In this case, the root test, I think, turns out to be easier, but either one gets you to the same place. In problem 2 here, an issue is, or kind of the big thing to focus on is we have sine here, And the problems that it causes are, one, sign oscillates, which makes any test where you take a limit difficult to deal with. What also happens is sign is positive and negative, and it keeps being positive and negative, so it doesn't on its own, kind of as is, really work with comparison tests. But what the problem asks for is show that this converges absolutely. And that means take this series, put on absolute values. 2 to the n is already positive, so the absolute values don't change that. But sign is positive and negative, so we do have the absolute values there. And before actually working this out, I'll say, even if this problem didn't say, show it converges absolutely, this would be a good route because you don't have a lot of tests that work. But if it was always positive, then you know some inequalities involving sign. So inequalities lead into doing a direct comparison. So the absolute values give us this positive series. And we know, so first we're kind of focusing on the top part of these fractions. The absolute value of sign is always positive because absolute values are greater than or equal to 0. And it's at most 1 because sign going between 1 and -1, its absolute value never gets above 1. So we know that inequality just because of how sign behaves. If we divide all 3 pieces by 2 to the n, 0 doesn't do anything. We get 2 to the n's here. And then what we can focus on is 1 over 2 to the n, which is, after rewriting just a tiny bit, this is geometric. So that means that our series that we're looking at, absolute value of sign over 2 to the n, is smaller than 1/2 to the n, and that series converges because it's geometric. So the way we end is that this is an application of the direct comparison test, which means that the absolute value version of the series converges. But what is sort of restating this in the way that the question was asked, the fact that the absolute value version converges means the regular version converges absolutely. So these are equivalent statements, but we were really asked about the original version, and so that's kind of the phrasing that we want to end with. So there's really kind of 3 series that we check in here. First is the geometric one converges. By a direct comparison, the absolute value version converges. And then we can say, since the absolute value version converges, the original series converges and converges absolutely. Questions about that? So let's talk about the next one. So this problem is saying here's a series, and since it's positive and negative, there are really 3 possibilities for classifying this. And I left one of the words out. You can say that it conditionally converges, absolutely converges, and then diverges. So what these mean is diverges means it diverges. The sum doesn't exist. Absolutely converges means even if you put the absolute values on, it still converges. And then conditionally converges is the middle case where it does converge, but if you put absolute values on, it doesn't anymore. So this is the case where it really needs the positive and negative parts to cancel in order to converge. And when you're given a problem like this, there are, I think, two ways to start doing this. One is, or I guess the options are, check if the series itself converges, or check if the absolute value version converges. In this case, what I decided to do was, let's look at the original version. The original version is alternating, -1 to the n, and alternating series are, it's good to use the alternating series test, which means look at the non-alternating part of the sequence. So in here, we have -1 to the n. The other part is 1 over 3n minus 4. And the alternating series test is nice because what you do is take this, find a limit, it's 0. It's decreasing because the bottom is going up, which means the reciprocal is getting smaller. And that's all. Checking these two things means that the original series converges by the alternating series test. So that means that as the original series, it converges. But what we also need to check is that it converges, or we need to check if it converges absolutely. If you put absolute values on and look at that series, does it converge? And when you have an alternating series, if you put the absolute values on, the effect is it's just not alternating anymore. We lose the -1 to the n, the 3n minus 4 is positive, so that just stays like it is. And then you really start from scratch. Here's this series, how do I decide what happens to it? And in looking at this, you can say, well, the -4 doesn't do very much, and a multiple of 3 doesn't do very much. The important part of this series is that there's an n. And so we can say that compare this series to 1 over n, and 1 over n diverges. If you, I don't think the direct comparison test works, but if you do a limit comparison, so form the fraction out of the original series and the comparison series and take the limit. So flip and multiply to get the n on top. N over n, n's in the top and bottom, the limit is 1/3. Now you have to remember, what does 1/3 mean for the limit comparison test, which is different than what 1/3 means for the ratio or root test. So in this case, the third, we don't care that it's less than 1. What we really care about is that it's not 0. And since it's not 0, the series that we are comparing our series to, or this one, these two do the same thing. And since we know this converges, our series, or sorry, we know this series diverges, so our series diverges too. So what we proved is really that the original, the original series converges. But if we put absolute values on, that diverges. And that combination is what it means for a series to converge conditionally. So if you ever answer a question, this series converges conditionally, you have to have checked two series. The original one converges, but the absolute value version diverges. Questions about that, or this kind of problem? So we're almost out of time, but that's the bottom, come up here. Okay. So this series 10 to the n over n plus 1 factorial, looking at it, factorials almost always mean try the ratio test. The 10 to the n on its own says maybe root test, but the root test doesn't interact well with factorials or this kind of repeated multiplication. So the ratio test says take the original terms, 10 to the n over n plus 1 factorial. On the top, we add 1 to all the n's, so that 10 to the n becomes 10 to the n plus 1, n plus 1 becomes n plus 2 factorial. Flip and multiply, group things together. The 10s, everything cancels to just get a single 10 on the top. On the bottom, what is happening is that n plus 1 factorial is 1 times 2 times 3 and dot, 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 up to n plus 1, and n plus 2 factorial is 1 times 2 times 3, dot, dot, dot. And it does have an n plus 1 factor, but only because that's on the way to the n plus 2 factor. And so with these factorials, all of these factors cancel except the bottom has an extra 1. And that's where the n plus 2 comes from. And in this limit, the top is fixed, the bottom is going infinite, so that limit is 0. Okay, and we're just a bit over, but I want to do a quick explanation for this last one. So this is another one where we want to decide if this series converges absolutely or conditionally or just diverges. In the first example, we started with checking if it converged just normally as a series. Another option is look at the absolute value version first. And so if we do that, that means throw absolute values on. The bottom is positive, so the only thing that means is the top isn't alternating anymore. And in this case, you can do a direct comparison test. Now, you don't just want to write this, you want to kind of make sure that it's actually true. But here the denominator is bigger with the plus 1, and that makes the fraction smaller. So we have this inequality, and the series 1 over n cubed converges because it's a p series with p equals 3. You can also do a limit comparison test with this same comparison series, and the limit turns out to be 1, which is not 0. So what this means is that if you put absolute values on, that series converges, and that means the alternating version, the one we started with, converges absolutely. And in this case, we're actually done. If you put absolute values on and it converges, that gives you your answer. It's that it converges absolutely. If you made the other choice and started with the alternating series test, so you'd look at 1 over n cubed plus 1, that decreases to 0, so it converges by the alternating series test. But then that's not enough. If you check that it converges, you still have to check the absolute value version. And in this case, what you would see is that it also converges if you have absolute values. So your first check wasn't strictly necessary. What you can also do is, or kind of the third option we didn't see in these examples, is if you check the original series and your series just diverges, then you can stop. You don't have to worry about the absolute value case, because if the original series diverges it's also going to diverge if you put absolute values on. So that would be something like for the series that looks like, say, -1, or yeah, -1 to the n, and then 2 to the n. Oh, this is hard to write this thing divided by n. So in this case, if you looked at the non-alternating part, so if you looked at just 2 to the n divided by n, that goes to infinity. And so the alternating version also diverges. And if the terms of the series diverge, if the sequence diverges, it also diverges when you try to add them up. So if you're given a series like this, which, yeah, I'm not going to try to write that because that's just going to look gross. So for a series, if they just diverge, then you don't have to worry about the absolute value version because you've already come up with your answer. It's just if the original series converges, then you have to check, does it converge with absolute values on? Okay. Sorry for holding you guys over a little bit. If you have more questions, I can answer them and I can pull that screen back up. But if not, there's not a quiz, so you're done with calc, or at least there is no assignment due today, and I'll see you guys tomorrow.